We've been told our whole lives that space is the next frontier. But there's one mission that quietly exposes the uncomfortable truth behind that phrase. It's not a new rocket. It's not a glossy concept ship with cinematic trailers. It's a probe from the 1970s that just keeps drifting into the dark. Voyager 1 launched in 1977, and right now it's still moving outward, still sending faint data back to Earth. And when you look at what Voyager 1 has actually accomplished, you don't just feel proud, you feel uneasy because it reveals how the universe really prices distance. Not in money, in time, in physics, in patience. Voyager 1 is often described as the farthest human-made object. That's true. But the more important detail is what it represents. It's a real working ruler for deep space. Not a theory, not a simulation. A machine that has spent decades paying the cost of leaving home. So, if you've ever wondered what interstellar travel really means, Voyager is the most honest starting point we have. Today, Voyager 1 is traveling at about 7094. That sounds fast until you realize what it's racing against. After 48 years of nonstop travel, Voyager 1 is far enough away that a radio signal takes about 1 day to reach it. That distance is a light day. The distance light travels in a single day, which means even talking to Voyager isn't talking. It's sending a message, then waiting. And that's where the real question hits. If it took us 48 years to reach 1 light day, how long would it take to reach 1 light year? Stay with me. The next step is simple math, and it completely rewires your intuition. Remember when I showed you the last book? From that edition, I now have another book, and it exists for a very specific reason. At its core, this book is about one question. If we had to rebuild civilization from scratch, what would actually matter? I go chapter by chapter through ideas that shaped humanity. How we organize, how we cooperate, how we survive, and how we pass knowledge forward. Some sections hit me harder than I expected, like the pages on responsibility, about what we owe to each other when systems disappear, the spread of long-term thinking, how decisions echo far beyond our own lifetime, and the parts about forgetting, how comfort slowly erases the lessons that once kept us alive. This isn't just a book you read, it's one you think with. If you're interested in humanity, civilization, or self-improvement, this is a book that stays with you long after you put it down. It's also a great gift for someone curious, thoughtful, or asking bigger questions about the world. This edition reflects everything I believe is worth preserving, and that's why these ideas still matter. Now, if you want a piece of humanity you can hold, check it out through the link below and use the code INSANE for 10% off. We throw around light year like it's just a dramatic way to say far, but it's a distance unit, and it's one of the most ruthless distance units ever invented. A light year is not time, it's distance. How far light travels in a year. And since light is the fastest thing we know, a light year is the universe reminding you that even the best speed comes with limits. 1 light year is about 5,84 trillion miles. That's a number your mouth can say, but your brain can't truly hold. So instead of trying to feel the trillion, watch what it does to every familiar idea about travel. On Earth, speed shrinks the map. Faster ships turn months into weeks. Faster planes turned weeks into hours. We internalize that curve so deeply we assume it will eventually open the stars. Voyager 1 exists to show where that curve breaks, because out there, you can go fast and still feel like you're not moving at all. Here's a cleaner way to think about it. Compare distances inside one consistent mental model. In that model, Voyager 1 isn't gone. It's simply farther down the same street, still inside the sun's neighborhood. Now compare that to the nearest star system, not a distant galaxy, not a fantasy destination, just the closest neighbor. On that scale, the nearest star sits around 4.2 light years away, about 4.6 trillion. Between here and there, there's no scenery, no islands, no checkpoints. Just a vacuum so empty it feels abstract until you remember that vacuum is filled with radiation and sprinkled with dust. At high speed, even dust becomes dangerous. Over a long time, radiation becomes relentless. Now, here's the point most people try to mentally look away from. Voyager 1 reached a lightening in about 48 years. A year has 365 days. So to estimate 1 light year at Voyager speed, you don't need advanced physics. You multiply 365. That comes out to roughly 7,500 years for 1 light year. Let that sink in. 7,500 years isn't a long trip. It's longer than most recorded history, longer than most civilizations stay recognizable. And the nearest star system isn't 1 light year away. It's about 4.2 light years away. So at Voyager speed, you're looking at roughly 74,000 years to reach the nearest neighbor. That number is so big it doesn't just challenge technology, it challenges planning. How do you build a mission that outlives every institution that could support it? How do you preserve knowledge, purpose, and maintenance across time scales where cultures reshape themselves? And here's the second layer, the part that turns this from a sad statistic into a hard limit. Durability. No machine we've ever built is designed to operate for 74,000 years. Power systems degrade. Materials fatigue. Memory fails. Radiation slowly rewrites electronics. So even if a probe crosses the gap, it won't arrive as a functioning explorer. It arrives as a silent artifact, a fossil in motion. This is why the phrase, "we just need better rockets," is a trap. Better rockets matter inside our solar system. That's where travel still fits inside careers, budgets, and political cycles. Between stars, the enemy isn't only fuel, it's time. A starship isn't just a vehicle. It's a system that has to stay reliable across eras where no one can come fix it. It needs navigation that stays accurate for decades, hardware that survives radiation for decades, software that doesn't become fragile over years if it flips and component drift. And it needs a mission that still matters when it arrives, because arrival is always later than you want. Every extra year multiplies the way something can fail. At this point, people reach for the generation ship idea. If a single lifetime can't do it, you send to society a habitat where the mission is passed down. It sounds like determination, but determination isn't the same thing as stability. Try to keep 5,000 people healthy, cooperative, and psychologically stable inside one closed system for 74,000 years. That's not just engineering. That's politics, culture, conflict, and meaning forever. On Earth, entire civilizations can transform beyond recognition within 500 years. Languages can drift dramatically over 1,000 years. So, after 1,000 years, the original mission is already a legend. After 20,000 years, it's an origin myth. By 50,000 years, the destination may feel like a story no one truly believes. A mission without belief becomes drift. And drift is how projects die, even if the hardware survives. All right, let's go to the optimistic extreme. Let's assume we reach 10% of the speed of light. That's about 67 and 9 milli-H. At that speed, the universe gets violent. Dust becomes a threat. Tiny particles become projectiles. But even with that speed, distance still collects its fee. At 10% light speed, 1 light year takes about 10 years. So 422 light years becomes 42 years one way. Then reality arrives. You need to slow down. You need time at that destination. You need redundancy. And if anyone expects return data, rescue options, or a trip home, your timeline stretches. That's how you land in the range of 90 to 100 years. Even with near miracle propulsion, the nearest neighbor is still a lifetime scale commitment. Now widen the target to something 40 light years away. At 10% light speed, that's about 14 years. And that pulls you right back into multi-generation planning again, even after you solve propulsion. Now for the twist that makes the scale feel even heavier, people often say Voyager 1 left the solar system. In one sense, it has. It crossed the helipause and entered interstellar space. But the solar system is more than the planets. It's the full gravitational reach of the sun. The Oort cloud is thought to begin somewhere between 2,000 and 5,000 astronomical units, and its outer boundary may lie between 10,000 and 100,000 astronomical units. At Voyager 1's current pace, it won't reach the inner edge for about 20 years, and it won't clear the outer edge for maybe 20,000 years. So, in a meaningful sense, our most distant probe is still traveling through the sun's outskirts. This is where the where is everybody question starts to sound less like mystery and more like logistics. If typical separations between civilizations are 1,000 to 2,000 light years, even communication becomes slow and fragile. Even light turns conversation into a message that outlives the people who sent it. Space doesn't connect. Space isolates. Voyager 1 will keep drifting long after its instruments go quiet. In about 14,000 years, it will pass relatively close to another star, close only by cosmic standards. By then, everything that launched it will be unrecognizable. And that leaves us with the one conclusion that actually matters. There is no easy interstellar plan B, not on human timescales, not on civilization timescales. If we want a future, it starts here, because the universe is not built for quick escape. But before we dream about reaching distant stars, we still haven't conquered our own solar system. Every planet out there is waiting to destroy our spacecraft in a different way. Mercury's extreme temperatures, Venus's crushing pressure, Jupiter's deadly radiation. Watch our video on what makes every planet in the solar system so dangerous to explore, and you'll understand why interstellar travel is even further away than you think.